Good afternoon. So today we're going to be teaching um, rational and proportional relationships, of course, but in today's lesson is going to be motivating and defining ratio and proportional relationships. Let's dive into the theory, okay? Okay, I wanted to think about this problem first. Do you think the mixture A, this one here, will be as the same taste and color of mixture B. Mixture B are all this here, right? So as you can see here, they have a kind of the same one red cup and three green as the same mixture, but also two more red cups and two more green cups. Do you think that those two mixtures are having the same taste and color? So before answer this, let me show you the theory, okay? So here's the theory. You can see the two aspects of those mixtures in two ways. You can be in the aspect of ratio and the aspect of quantity. For example, this mixture here has one batch. You can say it's 1 liter, and this other one here has four batches. One, two, three, four. This is one aspect of those two mixtures. They have different quantities, right? And also you can evaluate them by the ratio. So this one has 3 parts of grape juice and 5 parts of peach juice. So this is the proportion of 2 to 5. I mean 3 to 5. 3 grapes to 5 peaches. And also as you can see here, the other mixture also has the same ratio. 3 parts of grape to 5 parts of peach. So by having the same ratio, we can say that they have the same color and the same taste, even though they have different quantities of the substance. Now, try to see this for yourself now. What can you tell me about 5 meters in 2 seconds and 50 meters in 6 seconds? Is there something in common between those two measurements? So it's not easy to, it's not difficult to find out that it's the same thing that the last one. So here we have one batch of 5 meters and here one batch of 2 seconds. So the ratio here is 5 meters to 2 seconds. And also we can see here the same ratio, 5 meters to 2 seconds, only different quantities. Here we have more batches. So 3 times 5 is equal 15 here. And 3 times 2 is equal to 6. So 15 meters in seconds is as the same as 3 batches of 5 meters into 3 batches of 2 seconds. So they have the same ratio. We can say that those two people are running at the same speed, even though the third people here, the second people here are running more distance, right? So we have different batches only, but the same ratio. Now, here's a table that you can put those things together. For example, here's the view in batches. So the first batch is 3 parts of grape, 5 parts of peach. So we have 1 liter, so divided into 3 parts of grape, 5 parts of peach. So if you add another batch, it means that you add 3 parts of grape more 5 parts of peach. So here's the second liter, here's the third liter, here's the fourth liter, right? So here's the number of batch. So always times you multiply the batch by the numbers of parts of grape and parts of peach. So keep the same ratio, right? Now it's very easy to answer this question, right? So do you think that mixture A and mixture B will have the same taste and color? So the answer is obviously no, right? Because the second batch is different than the first one. So the first, for example, they have one batch of 1 red cup and 3 green cups. But the second batch is 2 red cups and 2 green cups. So they are different. So actually they are changing the color and the taste of the juice by adding the second batch that is different from the first one. Okay, now suppose you have 4 cups of red punch and 12 cups of lemon lime soda. Make a math drawing showing how to organize those cups so that you can tell from the way the cups are organized that this mixture will have the same flavor and color as mixture A. So you have to think that sometimes when you organize your data better, you can visualize better how to solve the problem. For example, if I give you scrambled data, you can look at and see nothing on it. But if they are organized, you can see right away what's going on. In this case, as answer for this problem here, it would be like this. If I give you those 12 cups, 12 lemon lighter cups and 4 cups of red punch organized like this, you can see they have 4 batches, right? The 4 batches equally to each other. So you can see the batch is composed by 1 red and 3 green, and you have 4 of them. So just because organizing data makes things easier for you to understand the problem. Now suppose you have 4 identical containers, 1 red punch and 3 lemon lime soda, all poured to the same level. So as you can see here, the same level. So you are about to mix them in a pitcher, and when you decide to make a large or a little bit more. So with this large amount to have the exact, you want this large amount to have the exact same flavor and color. How can you do that? How the mixture will compare to mixture A? Some people get a little bit confused when I said here all pour to the same level. So the answer for this question is, as long as you add 1 part of red punch for 3 parts of lemon lime soda, you will have the same juice. For example, if you add this kind of red punch here, you have to add 3 lemon sodas at the same level. But if you add 1 full cup of red punch, you have to add 3 full cups of lemon lime. As long as you keep 1 part to 3 parts, you're keeping the same ratio. So you're not altering the composition of the juice. Find out find mixtures of red punch and lemon lime soda that taste the same as mixture A. So the question here is, I give you the mixture A and give you the mixture B. So this is the proportion for the mixture A, 1 to 3, and mixture B, 3 to 5. I want you to complete those columns here, so as you can have the same composition of the juice. Okay, so you can pause the video and try to do it for yourself, but I'm just going to skip to the answer already. So for example, if you add another batch here, for 1 you add another 1 plus 1, 2. If you have 3, you add another 3, now 6. So a juice with 1 to 3 is the same juice as 2 to 6. They only have more quantities here, right? Here have 2 batches, here have 1, but the ratio is the same. So you can tell yes, that the juice is the same from the column 1 for the column 2. So if you add another batch, 3 to 9, it's the same juice as 1 to 3, only more quantities. So you can do multipliers, right? Multiples. So you can have the same juice. So you can tell that all those 4 compositions here are the same mixture A. We can do this for the mixture B. For example, here I'm not adding another batch, adding more 3 and adding more 5. So 6 to 10. And here 9 to 15, all the same mixture B. My question is, how can you compare mixture A and mixture B in regarding which one has more red punch and which one has more lemon lime? For example, if you only have the first column here, it's going to be very hard to compare because there is no matching number. Let me show you what I mean by matching numbers. Okay, this is what I mean by matching numbers, okay? So here in the third column and in the first column, you find that both of them has 3 cups of red punch. So it's easy to compare. For the same amount of red punch, as you can see, you have more lemon lime in the mixture A, have 9. Here you have 5. So as you can say, the mixture A has more lemon than mixture B. But there's another way that you can, there's another column that you can also match. For example, the 15 here. So here you're matching the lemon lime. So both of them has 15 cups of lemon lime. So you can match those 2 columns. So for the same amount of lemon lime, as you can see here, you have a mixture B has 9 red punch. So more than mixture A. They only have 5 red punch cups. So by doing those multiples, you can find a matching column for at least one number has to be equal so you can compare the other. So it's be much easier if you compare column 1 with column 1. They don't have matching numbers, right? Okay, let's see this. Recipes are something that's described in terms of parts, such as mixing 1 part of rice with 3 parts of water, or one mixing part of cement with 2 parts of sand and 4 parts of gravel. So in this case, 1 part could be any size we like. It could be the small size if container, or if it could be if you want a more of a large sizer, right? Larger size. Oh, sorry. So, for example, if you want a small cake and you put 1 egg and 1 cup of flour as the recipes tell you to do. So if you want a cake 10 times bigger, how do you do it? For example, you put 10 eggs and 10 cups of flour. So you add more batches. So the size of the part doesn't really matter. The matter is the proportion of the size. So you add more batches, you get more quantity of the same thing as long as you keep the proportion, right? In the case of a cake, 1 egg for 1 cup of flour, you put only more batches. 10 eggs with 10 cups of flour. Now we can see that we could see the problem in 2 ways. We can view in batches and we can view in cups. This is a different way of seeing the problem, the same problem. For example, here we're seeing the batches, right? Here's 1 batch or maybe 1 liter. So every 1 liter is divided by 3 parts of grape juice and 5 parts of peach. So you can add more batches as long as they have the same proportion. They're having the same you're adding the same quantity. I mean, you're adding another quantity of the same juice, right? So now the views in cups is a little bit different. So every cup has to have the proportion of 3 to 5. 3 parts of grape and 5 parts of juice. It might be a little bit confusing for you right now because, well, we're talking about the same proportion even in batches or in cups. But a better slide for you to understand this is this one here. So here are we viewing batches, right? This is one whole thing and the proportion is 3 to 5, right? Here's 3 parts and here's 5 parts. And the view in cups, we see every cup, right? You have 8 cups and 3 of them are red punch and 5 of them are lemon lime. So this is the 2 different views of the problem. A relationship between 2 quantities is called a proportional relationship if all coordinated pairs of value of quantities are in the same ratio. So they are only proportional relationship if they keep the same ratio. So we can think the pairs of quantity in a proportional relationship as varying together. For example, if a person walks 5 meters every 2 seconds, then the person walking times and distance are in the proportional relationship. So the person walking time and walking distance varying together. As time changes, so the distance. So namely every 2 seconds increase in time correspond with a 5 meters increase in distance. So working with a proportional relationships lays the groundwork for understanding the concept of slope, rate of change, and linear functions. We're going to be seeing this in the next lectures, but this is laying the ground and the foundation for those types of concepts. So here it is proportion relationship, okay? So 14 cups of flour with 4 cups of milk. And it's a proportional or the same ratio as 7 cups of flour with 2 cups of milk. As you can see very easily, right? 14 is the double of 7 and 4 is the double of 2. So they're equivalent ratios. They have the same ratio even though the different quantities. Now let's think about this in fractions. Proportion is often described as a statement of 2 equivalents such as 7 to 2 equal 21 to x, right? So let's find out who x is. So for example, if you multiply 7 by 3, you got 21. How much you have to multiply 2 to have a proportional relationship? For 3. So have to multiply 2 by 3 is gonna find 6. So 6 is the only number who make this a proportional relationship. Any other number here would not make this a proportional relationship. Other way to find out is to say that using a cross multiplication. For example, 7 times x equal to 2 times 21. So you can find x by saying x is equal to 2 times 21 divided by 7. So you find 6. Solving a proportion is the process of finding the unknown value in a proportion in which the other three values are known. Now let's do some exercise to see how well you did understand. So what I wanted to propose to you is you can try to solve that yourself, so you can pause the video, but for me to not losing time, so I'm going to skip into the solution, right? But if you will learn much better and fix the knowledge if you stop the video and try to do yourself first before seeing the answer. But let's see the answer now. So describe mixtures of liquid soap and rose water in the ratio of 5 to 2 from the multiple batches perspective and from the variables part perspective. So remember when I talk about the batches perspective and variable parts using that slide that show one batch and 7 cups. So it's the same thing. So I'm asking you to show me how to describe this relationship in batches and in cups. From the variable part perspective, we can draw this diagram stick. So we have here 3, 4, 5 parts of liquid soap with 2 parts of rose water. So the mixture are made where all the parts are the same size. As you can see, every block here has the same size. It can be size of a full cup or a full container. Doesn't matter as long as we keep the same proportion, right? So it could be 5 drops, 12 cups, or 3 gallons, or any other amount, as long as they keep the same proportion. So this is the variable parts perspective. Now the multiple batches perspective is we think the point of view, we think of the mixture as made of certain numbers of batches. But the batches is the same in the variable parts, they have the same proportion, right? So since the proportion is 5 to 2, you have to divide one batch in 7, and 2 parts would be rose water and 5 parts would be liquid soap. But here we see a whole amount together as one batch. And here we see the 7 parts separated, so it's a variable parts perspective. So let's see now the second exercise. Lavender oil and bergamot can be mixed in a ratio of 2 to 3. Give 3 different examples of amounts of a lavender oil and bergamot that are mixed at the same ratio. So here are the 2 more examples, right? I'm just adding another batches. So 2 parts of lavender oil and 3 parts of bergamot. So I add another batches, so 2 becomes 4. I'm adding another batch here, and 3 becomes 6. So I keep adding another batch to find out the 3 examples that the exercise is asking for. But in each example, there are 2 parts of lavender oil for every 3 parts of bergamot. So we're keeping the ratio, so where all parts are the same exactly size, right? So the same size of this little block here. Another exercise. Let's do the same thing. So you pause the video and try to solve yourself first. But I'm going to solve it right now. So use the ratio table to determine 2 ways which of the 2 snails are moving faster without using fractions. Explain your reasoning clearly in your own words. So the snail A is moving 3 inches in every 2 minutes, and the snail B is moving 4 inches in every 3 minutes. So I do the same thing that I wasn't explaining before, right? I'm adding another batches to find multiples for the snail A and also find multiples for the snail B until I find the matching number. For example, here we match number 6. So for every 6 minutes, the snail A is moving 9 inches. And for every 6 minutes, the snail B is moving 8 inches. So as you can see, snail A is moving faster, right? 1 inch for every 6 minutes. But before you find the matching here, it's going to be hard to compare 3 inches with 2 minutes with 4 inches with 3 minutes. So add multiples, we can find the matching number right here. In this case is number 6. So for the same amount of time, 6 minutes, we find that snail A is moving 1 inch more than snail B. Okay,